properties of logarithms. All right, so let's work with the properties of logarithms. So recall that logarithms are just exponents. So it shouldn't be too surprising that logarithms have some very useful properties that can be derived directly from the definition and the laws of exponents. So let's establish the properties of logarithms. So we're going to show that the log base a of 1 equals 0. So y will set equal to the log base a of 1. Okay. We'll rewrite this as an exponential statement. So a to the power y equals 1. Okay. We'll then set both sides with the same base. So a to the power y equals a to 0. Then now that we have the same base, we can drop the bases and set the powers equal to each other. So y equals 0. Therefore, the log base a of 1 equals 0. Okay. So now we're going to show that log base a of a equals 1. So we'll set y equal to the log base a of a. Rewrite it as an exponential statement. So a to the power y equals a. Okay. Now a is equivalent to a to the power 1. Now that I have the same base, set the powers equal to each other, y equals 1. Therefore, log base a of a equals 1. So summarizing the results of this example, we have the following logarithm properties. The log base a of 1 equals 0, and the log base a of a equals 1. For example, log base 7 of 1 will equal 0. The log base 1/2 of 1 will equal 0. The log base 8 of 8 will equal 1, and the log base square root 2 of square root 2 will equal 1. So in these properties, m and a are positive real zeros, where a does not equal 1, and r is any real number. So the number log base a of m is the exponent to which a must be raised to obtain m. That is, a to the power log base a of m equals m. The logarithm with base a of a raised to a power equals that power. That is, log base a of a to the power r equals r. Both of these properties are a result of the fact that exponential and logarithmic functions are inverses of each other. So let's now use these properties in an example. So 3 to the power log base 3 of 12 will equal 12. Log base 0.25 of 0.25 raised to the power 8 will equal 8. And e to the power natural log square root 3t will equal square root 3 times t. Okay. Other useful properties of logarithms are given next. So in these properties, m, n, and a are positive real numbers. A does not equal 1, and r is any real number. So the log of a product equals the sum of the logs. So log base a of m times n equals log base a of m plus log base a of n. The log of a quotient equals the difference of the logs. So log base a of m divided by n equals log base a of m minus log base a of n. The log of a power equals the product of the power and the log. So log base a of m to the power r equals r times log base a of m. Okay, so we can utilize these properties to condense and expand logarithms, which we will be doing shortly. So, for example, log base 3 of 7x equals log base 3 of 7 plus log base 3 of x. Log base 5 of x divided by 3 equals log base 5 of x minus log base 5 of 3. And log base 5 of 12 to the power x equals x times the log base 5 of 12. One result of these properties is the ability to rewrite an exponential expression with a base other than e as an equivalent expression with a base e. So a to the power r is going to be equal to e to the power r times the natural log of a. For example, the square root 3 to the power x equals e to the power x times the natural log of the square root 3. Okay. Objective 2. Write a logarithmic expression as a sum or difference of logarithms. So logarithms can be used to transform products into sums, quotients into differences, and powers into factors. Such transformations are useful in certain calculus problems. So we're going to refer to the previous pages to review the properties that allow us to do this. So first we're going to write a logarithmic expression as a sum of logarithms. So we're going to write log base a of x to the third times the square root of x plus 1, where x is greater than 0, as a sum of logarithms, and we're going to express all powers as factors. Okay. So we have the log base a of x to the third times x plus 1. All right, so we have two factors being multiplied by each other. We have x cubed and the square root of x plus 1. Since we're multiplying, we can think of this as an m and an n, so m times n. Now, if we have two factors being multiplied, it is the same thing as the sum. So we have the log base a of x cubed plus the log base a of the square root of x plus 1. Okay. Now we can rewrite the square root of x plus 1 as a power. So let's do that. Because the square root is the same thing as a power of 1/2. Okay. Now our direction says to express all powers as factors. So we're going to take our powers and we're going to move them to the front. So we'll have 3 times the log base a of x plus 1/2 times log base a of x plus 1. Okay, and that is our single log expanded into a sum of logs. So now let's write a logarithmic expression as a difference of logs. So we have our single log base a of x cubed divided by x minus 4 squared. So this is like m divided by n. So this will be the same thing as log base a of x cubed minus log base a of x minus 4 squared. Okay. Similarly, we have to express all powers as factors. So we're going to move our powers to the front. So 3 times log base a of x minus 2 times log base a of x minus 4. Okay. And now we've written our single log as a difference of logs. Okay. So now we're going to write a logarithmic expression as the sum and difference of logs, and we want to express all the powers as factors. So we're going to start off with our single log, so log base a of x plus 3 squared divided by 5 times the cube root of x minus 1. Okay. So when you have a rational expression like this, the first thing you want to do is to split up your log using the difference of logs first, and then apply the sum of logs. So we are going to take the log base a of x plus 3 squared minus the log base a of 5 times the cube root of x minus 1. Okay. Now we can split up this second log using the sum of logs. So we'll still have log base a of x plus 3 squared minus log base a of 5 plus log base a of the cube root of x minus 1. Okay. Now we can rewrite this cube root as a power. So log base a of x plus 3 squared minus log base a of 5 plus log base a of x minus 1 to the power 1/3. Okay. We can now just drop these brackets by distributing this negative sign. So that's log base a of x plus 3 squared minus log base a of 5 minus log base a of x minus 1 to the 1/3. Now all of our powers, we can turn them into factors. So 2 times log base a of x plus 3 minus log base a of 5 minus 1/3 times log base a of x minus 1. Okay. Awesome. Objective 3. Now we're going to write a logarithmic expression as a single logarithm. So another use of the logarithm properties is to write sums and or differences of logarithms with the same base as a single logarithm. So this is necessary to solve certain logarithmic equations, which we'll discuss later. So in our last objective, we took a single logarithm and we expanded it using the sum and the difference properties. And so now we're going to take logarithms that are being added and subtracted from each other and combine them into one single logarithm. Okay, so this is the condensing method. So we're going to write each of the following as one single logarithm. The first problem here, we have log base a of 5 plus 3 log base a of 2. Note that we not only have factors in the front of our second log, we are also adding 2 logs together. So that's going to be the sum property, meaning we're going to be multiplying an m and an n together. Okay, so first let's move our factor to the power location. So this is going to be equal to log base a of 5 plus log base a of 2 raised to the third power. We can simplify that. So log base a of 5 plus log base a of 8. 2 to the third is 8. So now we can combine log base a of 5 times 8, which equals log base a of 40. So now we've combined the 2 logs being added together into one single log. Let's do B. All right, we have a factor here. We're going to need to move to the power, so let's do that first. So 3/4 natural log 16 minus natural log 3 squared minus 8. We can also simplify this 3 squared as well. So we'll have the natural log of 16 to the 3/4 minus the natural log of 3 squared minus 8. Now we can simplify all the powers. So the natural log of 8 minus the natural log of 3 squared is 9. So 9 minus 8. So that'll get us the natural log of 8 minus the natural log of 1, which we can combine to the natural log of 8 divided by 1 because it's subtraction, which will get us the natural log of 8. Okay, yay, this is fun. And C, log base A of x squared plus 4 plus log base A of 7 plus log base A of x minus log base A of 4. Okay, so we're going to take this in piecemeal one at a time, and we're going to go from left to right and just start combining logs together. Okay, so the first one is going to be these two logs, which is being added together, so we're going to multiply these two together. So log base A of x squared plus 4 times 7 plus log base A of x minus log base A of 4. Okay. And we then can combine these two logs together. It's being added, so we're going to multiply. So log base A of x squared plus 4 times 7 times x minus log base A of 4. Okay, so now we only have two logs and it's being subtracted, which means we're going to divide these two. So log base A of 7x times x squared plus 4 divided by 4. And so now we have our single log. Ooh, that was beautiful. We can simplify that numerator. So we'll have 7x cubed plus 28x divided by 4. Okay. All right. So some things to caution yourself when working with logarithms. There are several common errors that some students make with common logs. Okay. So they think that the log base A of m plus n is equivalent to log base A of m plus log base A of n, which is incorrect. When two factors are being multiplied together, then you can split them up using addition. Log base A of m minus n equals log base A of m minus log base A of n, which is incorrect. When your m and n is being divided, then you can split up your log by using subtraction. And log base A of m, the whole log raised to the power m, is the same thing as r times log base A of m. Now note the only part that's being raised to the power r, which then allows you to move that power to the front of your log. Okay, so just some common things to keep in mind when working with your log properties. So two other important properties of logarithms are consequences of the fact that the logarithmic function y equals log base A of x is a one-to-one function. So in these properties, m, n, and a are positive real numbers and a does not equal 1. So if m equals n, then the log of a of base A of m equals the log base A of n. If log base A of m equals log base A of n, then m equals n. For example, if 3 to the x equals 8, then the log base A of 3 to the power x equals log of A base A of 8. If log base A of 4x equals log base A of 16, then 4x equals 16. Okay, so these properties are useful in solving certain exponential and logarithmic equations, which we will discuss later. Okay, but objective 4, evaluate logs with base is neither 10 nor e. So common logs are usually abbreviated by writing the log with the base understood to be 10, just as natural logs are abbreviated ln with the base understood to be e. Common logs were used to ease arithmetic computations before calculators became commonplace. Natural logarithms remain important because they are used often in the study of natural phenomena. Most calculators have both a log and a natural log key to calculate the common log and the natural log of a number, respectively. However, how do we approximate a logarithm with a base other than 10 or e? And we'll explore this in our following example. So here we're asked to approximate the log base 4 of 17 and round the answer to 4 decimal places. So to do this, what we're going to do is we're going to set this expression to y. So we'll have y equals log base 4 of 17. Setting this expression to y gives us a log statement, which will then allow us to rewrite this as an exponential statement. So we'll have 4 to the power y equals 17. Okay. All right. So noting that we have a base 4 and a base 17, and we cannot convert any one of the bases to look like the other, we can then apply one of the properties of logs to help us. So we are going to apply the natural log to both sides of our exponential statement. So we'll have the natural log of 4 to the power y equals the natural log of 17. Okay. This will allow us then to use other properties of logs in order to solve for y. So we can move the y to the factor location. Okay. This will then allow us to divide both sides by the natural log of 4. Okay. Now we can enter that expression into our calculator to get an approximate value for y. All right. So we'll take the natural log of 17 divided by the natural log of 4. Okay, and press enter. All right, so we're rounding to 4 decimal places, so we'll have 2.0437. So that is the approximate value for our log base 4 of 17. So this example shows how to approximate a logarithm whose base is 4 by changing to logarithms involving base e. And we did that by applying the natural log to both sides. This approach can be generalized with the change of base formula given in the following theorem. So this theorem says that if a does not equal 1 and b does not equal 1 and m are positive real numbers, then the log base a of m equals the log b of m divided by the log b of a. Because most calculators have keys for both log and natural log, in practice, the change of base formula uses either b equals 10 or b equals e. So we can either have log base m divided by log, not base, log m, because the base here would be 10. Log m divided by log a, or we can have the natural log m divided by natural log a. So either one will get you close to your answer that you can use. Okay, so I'm going to show you that here. So we're asked to approximate and round the answers to 4 decimal places. So here we have log base 7 of 29, and I'm going to show you both for log and natural log so that you have it in your notes. So we know we'll have log, if we're doing common log first, we would have log 29 divided by log 7. And then we would enter that into our calculator. Or we can do natural log 29 over natural log 7 and enter that in our calculator. So let's do that. Alrighty. So we'll start with our fraction. So log 29 divided by log 7. We get a value. Now let's do the natural log. Natural log 29. Natural log 7. Okay, awesome. And we get the same values. So 1.7304 rounded to 4 decimal places. All right, let's do the next one. Okay, so we have log base pi square root of 11. And we'll do both, the common log and the natural log. So we'll have log square root of 11 divided by log of pi. And then we'll have the natural log square root of 11 divided by the natural log. Ooh, there's no square root for that. Natural log of pi. And we'll get approximated values. So let's enter those into our calculator. So we'll have log square root 11 and then log pi. Okay, and then we'll do the natural log square root 11 and then natural log pi. All right, and we got the same values. So to 4 decimal places, we have 1.0474. All right, so whether you do natural log or log, you'll get the same value. All right. Objective 5. Okay. So the change of base formula can also be used to graph logarithmic functions whose bases are neither 10 nor e. Okay, so we're going to use a graphing utility to graph y equals log base 5 of x. So we can either graph the natural log or the common log to obtain this graph. Okay, so note that we're using the change of base formula to express y in terms of logarithms with base 10 or in base e. Okay, so let's pull up our calculator. And I'm going to move it over a little bit. Okay, so we are going to go to y equals, and we are going to place our natural log x divided by natural log 5. And we will then do zoom, and we want to fit it. So that'll be 0. All right. And so now we have the graph of log base 5 of x. So that's how you graph a log in your calculator when your base is neither 10 or e. Okay. Awesome. Well, that concludes section 4.5.